Hello, everybody. First talk after the break is going to be by Andrew Godwin. He's going to talk to us about all the things we do wrong in IT and that can look at aviation and see how they solve all the problems in the past. Give him a round of applause.
Thank you, Marcus. Hello, good morning, everyone. So this talk is titled You Have Control. I'll get to what that is later, but it is about trying to learn lessons from aviation. So a little bit about myself first. I am Andrew Godwin. If you're unfamiliar with me, I am a Django core developer, most famous/infamous for migrations and channels and things of that nature. My day job is at Eventbrite, and in my spare time, one of my many hobbies is being a private pilot. I've been a private pilot for about, I'd say, 5 years now. I learned when I was living in London before I moved to California. And when I moved to California, I was like, oh, well, there's even better weather here and much less clouds, and it's 1/3 the price. That helps things a lot. Before I continue, this talk has some difficult topics in it, so there's a content warning. It has a very frank discussion of death and accidents. If this affects you, this is throughout the entire talk, I'm afraid, so just be aware of that. So let's start with software. Software is very difficult. If you don't believe this, then either congratulations, you're a genius, or you haven't been around long enough yet. I used to think it was easy about 10 years ago. But perhaps my favorite thing is that this is not just true of software. My favorite blog series in the world is an unfortunately short one called Things I Won't Work With by Derek Lowe. Derek is an industrial chemist. And he had a wonderful series of talking about various horrific chemical combinations that he was continuing to amuse people have managed to make. My favorite one is titled Sand Won't Save You This Time, about a reader who asks, well, is there any substance in the world that can make sand be on fire? And he says, well, of course there is. And it goes on, and like my favorite thing is like, you end up with this thing called a metal fluorine fire, which sounds very bad. And then the only correct solution is to run away very fast. One of the fires in this article, I believe, burnt through 3 solid stories of concrete into a basement and then through the catcher in the basement and kept going for like, a good few hundred meters more. It's not great. So let's think about what things we have that are perhaps not particularly good in computing. I have a personal list of things I won't work with. It has things like Unicode, locales, time is terrible. Calendaring, no, can't do calendaring. Geography, that's also terrible. Money, none of this stuff, please. The list goes on. In short, it's all of everything in computing science. And so we have a difficult field. And we realize this. I think a lot of us in this room have been through problems at least one of those things and other things. And sometimes we feel alone. Sometimes we're like, oh, we're stuck in this world. We have these difficult problems in our ivory towers. But that's not true. Engineering is a general discipline. And there's many, many other forms of engineering. And in particular, aviation and aeronautical engineering has been here before. A Boeing 747 has 6 million individual pieces. Now, if you're comparing, none of my projects have this many lines of code in it, so I feel OK about that. The more impressive part is that those planes have a 0.000006% accident rate. They are incredibly reliable. In fact, I believe there's only 1 accident or 2 that contributes to that particular number. If you look at the overall numbers, airplanes are almost the most safe thing in the world. Trains are very slightly safer in terms of a form of transport, but they are on the ground on rails, and sort of there's no steering wheel or anything, just a forwards and backwards lever. Cars are much worse, and it turns out walking is even more dangerous, so my advice is don't go outside. If you're going to the airport, just go in some sort of like train device. So sorry people in Melbourne about that one. But the reality is, when we look at this, it turns out that it's not just the machines, it's not just the engineering involved that you might think about on a technical level. It's also the people. The causes of accidents, over 3/4 of accidents in aviation are at least partially caused by pilot error. This is often something people don't realize. People often think the mechanical portion of this chart would be much, much bigger. It turns out the mechanics are very good at their jobs, as are the engineers. And the main problem is you have these fallible human beings flying giant metal boxes of air and happiness across the sky, and sometimes things don't go perfectly well. But one of the interesting things is, even with this kind of accident rate, aviation is still incredibly safe. Aviation and engineering in general has taken those things and slowly, over many, many decades, knocked out every single one of the risk factors to make it safer and safer and safer. So one of the things I'm going to do here is go through 6 of those main aviation principles that I learned during my pilot training and talking with other pilots, other engineers in aerospace, mechanics, everyone in the field, and how we can start taking those and applying them towards software. So, first of all, let's talk about hard failure. One of the key things you learn when you start being a pilot is if an instrument goes wrong, say your compass is wrong or your altimeter stops reading correctly, you don't just ignore it. You put a piece of paper over it. In an electrical cockpit with screens rather than analog instruments, the computer will remove the instrument from the display and put a big red X in its place. There's a very strong hard failure in that case. This is because once something has shown itself to be untrustworthy, you should not continue to trust it. And this is true of not just instruments, but also the autopilots, engines even. If an engine starts running really strangely, you don't just turn it off, but you try and land and turn it off as soon as possible. Air conditioning, all this stuff in airplanes is life critical. And air conditioning in a plane is the thing that keeps you alive. But of course, this only works with redundancy. If an air conditioning pack fails in a plane, it turns itself off, but there's also 2 or 3 to take its place. And of course, you land immediately because you've lost your redundancy component. And this often manifests in software in interesting ways. How many of you have at one point uttered phrases like this, like, oh, well, we'll just ignore these errors. That way the site won't crash. Or, oh, well, we won't do full validation later. We'll just save the invalid data. We'll fix it later. These are fantastic ways to ensure you never fix the thing in question. I once got a great data set on a project I worked on about a decade ago of football pitches in the United Kingdom. Now, geospatial data is a wonderful thing, especially when it doesn't say what projection it's in. I eventually worked out it was the wonderful OSGB 36 projection. So if you know that in the room, congratulations. But of course, it wasn't perfect. There were errors. One football field was in Scandinavia, definitely not in the United Kingdom. Another one was several hundred kilometers off the top of the North Pole. That was a fun one. So it's really important to not just have good data, but to make sure it's valid on the way in. Something you'll see me say at work a lot, if you ever work with me, is like, any code review will be like, this error's not strong enough. Like, raise a traceback, get it into our traceback alerting system, let somebody know it's broken, just don't let it linger. Otherwise, it will be there for years and years and years. And this kind of comes into the second principle, which I call good alerting. In a cockpit, you only have a limited number of audio alarms. And cockpits, and cars at some levels too, are very, very selective about what sets off an alarm. There's only a few different tones. One tone means you're going to die. A different tone means your meal is ready. And they are very distinctly different tones. But crucially, they did some research. And once you get past 4 or 5 different noises, pilots couldn't distinguish them. They started forgetting what they meant. And so this has a thing that's called alert fatigue. It's not just the number of tones, but also if an alarm is constantly going off, your brain is very, very good at ignoring it. Your brain has developed an ability to ignore things that annoy you on a constant basis. This is very useful for things like pain. But it also means that if you get an email every day saying that this thing is broken, your mind will just slowly filter it out over time. You'll start forgetting about it. So one of the things you should do in this sense is try and have very strict levels of segregation, those different tones. I often do things like critical, normal, and background. Critical is, this is really bad. It has to wake somebody up. The crucial part of that is it must be actionable. If you wake somebody up and they can't do anything, you've failed. You have to be able to do something. If you can't do anything, it's not an alert. It's a bug in your application. You shouldn't wake somebody up. You should find whoever designed that in and make them design it out next week. Normal stuff is a bit more relaxed. Like, well, it's an error. It's pretty bad. But let's say it happens to, like, 0.1% of people, or it's only to people in a certain area, or it's just Australians. That's fine. And so that's the sort of thing you log, you look in your error logs, but you fix over a week or so. It's not critically important, but you should fix it. And then there's background stuff, things that are always breaking. For example, like, oh, you know, I work for Eventbrite. We're a very large company. We process a lot of money. A few transactions fail every day because that's just the nature of doing a lot commerce at that scale. Those for us are metrics. They're not errors. We have an expected level of failure of, you know, on a global scale, how many transactions won't work properly. That's not a thing we get error emails about. It's a thing we have as metrics. If you've been ignoring an error for a week, just turn off this error report. You won't miss it. You're already ignoring it. And everybody else who works with you will probably thank you. This then comes into finding your limits. One of the important things that I learned going into aviation was that we don't say if things will fail, we say when they will fail. Everything fails. The key is to know when it fails. Often you see this phrased as what's called MTTF, mean time to failure, or MTBF, mean time between failures. But in general, what it means is you do a lot of analysis and research. You take the thing you're testing and you break it again and again and again. One of my favorite pictures is this picture. This is from the Boeing factory in Seattle. This, I believe, is a 737 or thereabouts. The wings, you will notice, are not at a good angle. This is what's called the wing break test. Boeing deliberately take planes that are pretty much fully built on an airframe level and will just pull the wings up until they snap. And they'll do it again and again and again. They're not just, you know, trying to break planes for the hell of it. They're trying to work out what angle those wings get to before they fail. The design envelope for the plane is about 20 degrees of angle before they break. That's what the worst storm in history will flex a plane's wings to. These wings break at 55 degrees. That means you know you have an incredible margin of error between your design envelope and what you need to get to. And this is true of software too. You don't have to be able to perfectly scale to huge amounts of traffic from day one. If you're a small startup, you do not need to handle, you know, 10,000 requests per second. But what is important is to know where your limit is. If you know that your current infrastructure can handle, let's say, 100 requests a second, when you get to 50, you go, well, we've only got half of our buffer left. Now is the time to start the big product to improve our scaling. Don't wait till you get to the actual breakage point. Risk is very good when you're informed. Knowing when things break lets you take that risk in a very informed manner and understand how far along that path you are to things breaking. When you're doing big engineering projects, and as you get bigger into a bigger company, things just take longer, having that planning and that ability to look ahead in time and know when things are going to stop working lets you really understand how to plan things, how to prioritize things. And part of this, too, is not just planning around failure, but building for failure. It's not just good enough to, you know, say, like, oh, yeah, it's all going to break, and at some point, things will just go wrong. We don't take pilots and train them for, oh, well, we're training you for great flying. We're training you to fly in perfectly clear skies and no wind. That's it, training done, thank you, here you go. In an aircraft design, no single thing in the aircraft can take it down. As I mentioned before, it's full of redundancies. And this is because chaos is just part of the world, right? Things randomly break. Things break before their mean time to failure. There may be some sort of weird thing you didn't plan for, something out of specification, everything like that. And one of those things you want is this for our code as well. You don't want a site where if any one thing breaks, the whole thing dies. Because as your site grows in scale, you're adding more and more and more single points of failure. And inevitably, if your site relies on every single server being up, and you now have 100,000 servers, like one's going to break at least every day. Like machines are fallible, and as you get more of them, you will see those things become more real. How do you tackle this, though? Well, you tackle it the same way that we tackle it in other engineering disciplines. You actually fail things and see what happens. One of the fun things to do if you have, you know, at least a few servers, just kill the application randomly on a server each day. Netflix's Chaos Monkey is most famous for doing this. But it's a very good practice to do. Often it's referred to as something like crash-proof software. And it's not just servers or applications dying. One of my most favorite, really nasty things to detect is network failures. And not a proper full failure. No, 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 no. When it goes like, oh, it's 5 seconds latency. It's still there, all your monitoring says, oh, the connection's still up, but everything's really, really slow. And a lot of applications don't understand that middle point between things are good and things are entirely broken, and will just struggle on and spin up and use more and more resources and really jam themselves in the process. Another thing here, too, is unreliable connections. Now, again, Australia, so you're all familiar with this. The rest of the world can't talk to you very easily. But also, a lot of people these days use 3G or mobile phones for their connections to the internet. The number of times I've had an app on my mobile phone that doesn't work in situations where you get signal, it goes away for 2 minutes, you get signal again, it goes away. This is the London Underground, by the way. Just is astonishing. People just don't think about this. And as I said before, like the majority of pilot training is handling emergencies. Of my training, around 3/4 was my instructor just randomly turning the engine to idle, or saying, oh, you've lost your compass, and covering it up with his hand, or various other really nasty things like that. Because we're not there to practice flying. Like, flying is very easy. My very first flying lesson, I sat in the airplane, the instructor went, okay, you can take off. I was like, what? It's like, oh yeah, just pull out the throttle and pull back on the stick, it will just take off by itself. That bit is very easy. The thing they train you for is when you take off and then the engine fails. Or when you take off and go into the cruise and then the engine fails. Or if there's a fire. And one of the main ways we do this is checklists. This is an excerpt from my very first checklist from the plane I learned in, a Cessna 152. This is one of 3 pages of emergency handling. It's very easy to find. It's got this lovely big red striped border on it, so you can find it in the little booklet easily. And every single situation you might have, engine fire is right there, it has a simple checklist. Because it turns out when you're under pressure and when things are going wrong, the human brain is terrible at remembering precise instructions. But it's very, very good at reading them off a convenient piece of cardboard and doing them in order. And so, in the case of engine fire, you close the throttle, you pull out the mixture, you turn all the fuel ignition off, and then you do a forced landing. And it says, do not attempt to restart, because if it's been on fire before, it's probably be on fire again if you start it up again. And checklists aren't just good in aviation. They are good in other industries too. One of the most interesting developments is in medicine, where checklists have improved success rates for operations by a substantial amount. And it's also true for software. If you have software, it's going to fail at some point, if you're doing software as a service or hosted software at least. And that means you should be ready for it to fail. And being ready doesn't mean like making sure you've got some beer in the fridge or something like that. No, it means practicing it. You want to practice failure and go, OK, this week we're going to try turning off the main database for 10 seconds, see what happens. Obviously on a separate staging environment, not in the production one, please. But the point is your operations team or your SRE team or whoever's doing this should be ready to do these things. When the inevitable happens, the reaction shouldn't be, oh no. The reaction should be, oh right, we did this one last week. Right? It should be this practiced approach, this easy way of getting towards this stuff. That's one of the ways you start solving the greater complexity problem with people. But as I said, the problem is not just technical. These 4 previous points have been about mechanical, technical problems in particular. But human error is a big proportion of aviation problems. And I would argue a big proportion of engineering problems as well. One of the most important things, especially in large-scale engineering, is good communication. The title of this talk comes from when you hand over control of an aircraft. When you give somebody control of the plane, you tell them you have control. They then tell you back, I have control, and you confirm with them you have control. This is called positive transfer of control. This is a very important concept because this comes from a lesson where this didn't happen and the plane crashed, because both pilots thought the other one was flying the plane, and you can imagine what happened. This is not obviously quite as fatal in software, but as you work on bigger and bigger projects, as I've had the pleasure to do throughout my career, you'll get teams doing different parts of stuff, and more of them. And as you get more and more different teams, you'll find yourself talking to more people, and that nice bubble of, oh, I know what everything's doing, I know how everything happens, doesn't exist anymore. In fact, as you grow, communication becomes exponentially harder. If you've got a small team, you can happily sit in the room and over tea and just discuss what's happening between the 2 different parts of your application. But as you get bigger and bigger, the number of people you have to talk to literally exponentially increases. In an organization the size of the one I work in now, we have over 300 engineers. I cannot talk to all of them even once a month. We have to work on good communication. And that's not just having things like being able to talk to each other properly and training, but also understanding that you need to not know everything. You have to have people delegated to go and do communication. There's a reason we have good managers who go and handle that part for you. And also write everything down. I work with a team who works across 9 different time zones in 2 different primary languages, Spanish and English. Things written down massively reduce the number of meetings, especially when meetings between Madrid and San Francisco are at bad times for both parties. I do not get up at 8 in the morning, I'm sorry. I do once, but that's me. And then finally, it's very important to have a clear chain of command. One of the things you often find as you grow as a company is the previous sort of, oh, well, we're just going to make decisions as we go, and we're going to find the right person for the job stops working. You have to start having that clear idea of who makes decisions. And it's not just making decisions, it's making decisions when they're difficult. A lot of the time, there's never a correct answer. It's a skill I've learned over many years to be able to go, actually, neither of these is the right choice, but we have to pick one. And be willing to defend that one, at least to a point as you go on. Having consistency is more important. And this comes to the final point, which is blame culture. There was a big problem in aviation in the 70s and 80s. There's a reason I know all these stats. I've shown you the graphs. These graphs are sourced. You can see the citations in the earlier slides. Every single incident of an aircraft is reported and investigated by the national board of the country, usually, that the aircraft crashed in or the aircraft was from. And one of the key things we realized, starting in World War II and continuing, was that there's never a single cause of a problem. Problems always come from 2 or 3 sources you never expected. And often one of those is human error, but it's not the human's fault. You shouldn't blame them because you can do things to mitigate them. If you ever see a problem, you should make it very, very hard to do again. If an intern drops a production database, it's not just their fault. You shouldn't blame them. Why could they do that in the first place? Why did you have anybody with the access to drop the production database? Like even the main administrator should have to go through like a sort of war games, turn your key secondary kind of thing to get that to do. And one of my most favorite examples of this, and having been to Hawaii recently, is last year. When residents of Hawaii got this wonderful message on their phones telling them there was an inbound ballistic missile threat. Now this, as you can imagine, is very sobering and wakes you up very quickly. And the person who did this was fired and let go, or I think at least reassigned. Which is weird because like, this person is never going to make that mistake again. This is the most expensive lesson that person's ever going to have. And of course, you won't blame them when I show you the interface they'll be using. Now, you'll notice here, there's a lot of links. This link is different to this link. The top one is the real one. The bottom one is the drill one. The person in question just clicked the wrong link. They are the same size. They are on the same part of the page. For some reason, the really bad one is closer to the top, which is bad UX design. This is a case of it's very, very simple to stop this same thing happening again. But how do you encourage this? How do you get to a place of no blame culture, of improving yourself rather than pushing blame onto others? Well, it's important to encourage reporting. If things like this happen, you should have an open environment where people can come to you and say, yes, I screwed up, I'm sorry, here's what I did, here's how I did it, how can we stop this happening again? Sit down, have a post-mortem, go through those steps, and try and understand what happened, and use that person's expertise and their experience to fix things. Do not blame them. It's never just their fault. There are some people who are just, malicious actors. They're a different scenario, but in general, the people you work with, the people you volunteer with, whoever, pretty much have the best intentions in mind, and it's up to you to work with everybody to improve that experience for everyone, and so that next time it's not you who makes the same mistake. Now, of course, these 5 facets, these 6 facets are just a small part of the larger way we do design in aviation and aerospace in general. But there is one thing we say. A lot of these rules and regulations that apply to aircraft and everything like that, all those rules are written in blood. Every time there's a rule or a regulation, it's nearly always from a previous crash. Somebody has at least been injured, if not died, to bring you that particular piece of regulation. And you might think that software is not there yet. Well, unfortunately, we're a bit closer than I would like. I'll go through a few examples of where software has had this particular effect. I'm sure many of you are familiar with Margaret Hamilton. She was the lead on the Apollo program's software division. This stack of papers here is, in fact, the source code for the Apollo lunar module. Margaret Hamilton and her team invented basically real-time computing and watchdog recovery. The Apollo 11 lunar lander overloaded itself on descent. The number of interrupts from the downward-facing radar altimeter overloaded the computer and made it unusable. If it wasn't for the code that she and her team had written, which made the computer watchdog itself, reboot back into a basic recovery mode and continue basic flight functions, the astronauts would have died and crashed into the surface. This is a case of very, very good software because she knew what the hell she was doing. That's not the case for the designers of the Patriot missile. The Patriot missile is infamous because it used floating point numbers, always a good start. And it had a bug where, after it had been turned on for a certain amount of time, the floating point inaccuracies built up and built up and built up, to a point when it had been on for too long, it just got the position of the thing it was meant to hit wrong. So the Patriot, for reference, is a missile intercept system. It's a defense system. It's meant to shoot down incoming artillery to protect a base area, usually. And in this case, they left it on for too long. The floating point area built up, and it missed the missile, and it killed 28 people as a result. Therac is perhaps even more infamous. If you've not heard of Therac, congratulations. It's a very sobering read. This was someone's amazing idea to have a fully software-controlled X-ray machine. As a programmer, that sounds terrifying. The exposure and aperture of the machine were controlled purely by software. And there was a bug where, in a certain situation, the aperture would stay open and give the person underneath a lethal dose of X-rays. It killed at least 3 people. It severely injured at least 3 more. And the irony is, it had a hardware interlock. But in all their testing, it was very basic testing, not testing to destruction, the software worked fine. So they removed the hardware interlock in the final product for cost-saving measures. And that's the reason that the software, because the hardware interlock was what was saving things in tests. They removed it, it all went up. And of course, much more recently, we have the example of the Uber autonomous vehicle that saw a pedestrian, analyzed them, and wrote them off as not a threat and crashed straight into them. We have a lot of stuff in software that is getting increasingly involved with human lives. I would hope most of your software isn't, or if it is, that you are doing it correctly. I am always reassured that most of the stuff I write is not in a life-critical path. But as we grow, it's not just things that seem obvious, like driving or machinery. It's also things like social interactions. Like, we've seen the rise of extremism. Things we do as software engineers, algorithms, the way we show, the videos we show people on YouTube, all have an effect on people. And so as we go into the future of software, as we progress down the making big impacts in people's lives, let's maybe try and learn some of those lessons from aviation and take them forward and maybe build some of our own. Thank you very much.
Thank you, Andrew.
Thank you very much.
Token of appreciation from PyCon.
Thank you.
Next on stage here is Curtis Maloney, who gives us a short introduction into Python logging after a 10-minute break for room changes. Another round of applause for Andrew. Thank you.